Okay, ladies and gentlemen, welcome back to your video notes for Chapter 6 in your McGraw-Hill Geometry textbook. We're here to discuss Chapter 6, Section 3, which is entitled Tests for Parallelograms. There are a number of different ways for us to check a quadrilateral to see if it's a parallelogram. There are 4, in fact, appropriate mathematical tests to see whether or not a quadrilateral is, in fact, a parallelogram. The first thing you can do is check the definition of a parallelogram, i.e. you can check to see if both sets of opposite sides of the quadrilateral are parallel. Again, that's both sets are parallel. It has to be both. You can check to see if both sets of opposite sides of the quadrilateral are, and this is a typo, congruent. That would be the second. So if you can show that both sets of opposite sides are congruent, that's enough to guarantee that a quadrilateral is a parallelogram. You can check to see if the diagonals bisect each other. Again, the key there is both of the diagonals have to be bisecting the other. And finally, you can check to see if one set are both parallel and congruent. If one set of opposite sides is both parallel and congruent, that also is enough to guarantee that that is in fact a parallelogram. So this is going to come in a couple of different forms. The first form would be questions like these 3 here. What you need to do is you need to decide whether or not you are given enough information to guarantee that the shapes shown here are in fact parallelograms. And you need to justify your answer by explaining it using one of those 4 tests from the previous slide. So you can show either that both sets of opposite sides are parallel, both sets of opposite sides are congruent, the diagonals bisect each other, or one set of opposite sides is both parallel and congruent. So for instance, in number 1, this one's pretty easy. You can easily state that both sets of opposite sides are congruent, so the answer to this one would be yes, because both pairs of opposite sides are congruent. In other words, it passes test number 2 of 4. Okay, both pairs of opposite sides are congruent. Number 2, we've got one set of opposite sides are congruent, and we have 85-degree angles. But without any other markings, we simply don't know enough to guarantee. See, we don't know enough to state for sure that these other 2 sides are congruent, so we can't use both sets of opposite sides are congruent, and we can't guarantee without knowing one of these 2 angles whether or not the set of sides that is marked as being congruent is in fact parallel as well. So this would be an example of no, we simply don't have enough information to confirm. And if we cannot use one of those 4 rules, our answer has to be no, because we simply don't know enough to say yes. Finally, on number 3 here, we have enough to state that FG and JH are both 14 inches, that's congruent. And we also have enough to state that they have to be parallel as well, because if angle H is 80 degrees and angle G is 100 degrees, then the converse of the consecutive interior angle theorem would guarantee that FG and JH are parallel, because we have that converse that says, well, if a pair of consecutive interior angles like G and H adds up to 180 degrees, that means the lines being transversed, which would be FG and JH, those have to be parallel. So this would be a yes. FG and JH are both congruent and parallel. In other words, we're passing test number 4. Again, you have to be able to show one of those 4 is true in order to guarantee the answer to one of these questions is yes. All right. The other things we can do with this is we can say, okay, here's some information about a quadrilateral. What would we need to do to make it a parallelogram? So for instance, here we have FK is 3x minus 1, KG is 4y plus 3, JK is 6y minus 2, KH is 2x plus 3. Find x and y so that this is a parallelogram. Well, if we want it to be a parallelogram, then we have to, the diagonals would have to bisect each other. And I'm going with the diagonal rule because I have information about the pieces of the diagonals. So, in other words, what we're saying is that FK has to be congruent to KH, and JK has to be congruent to KG. Okay, that's what we're saying. In order for these to bisect each other, these pieces have to be congruent. Well, if they're congruent, then they're equal. So FK would equal KH, which means we can take those expressions from the directions. 3x minus 1 has to equal 2x plus 3, and we can use them to set up and solve equations for x and y. JK would have to equal KG, meaning that 6y minus 2 has to equal 4y plus 3, and we could solve those equations for x and y. And if these are the values of x and y that satisfy these equations, that would force our quadrilateral there to be a parallelogram. So we would go in here and we would solve these equations, and we would get that x would have to equal 4, and y, when we move the y to one side, we would get 2y equals 5. And we would divide by 2, and we would get a y value of 5/2. So in order for this to be a quadrilateral, we would have to have x is equal to 4, and y is equal to 5/2. So that's the second problem type we could see here. And then finally, we have, well, here's a couple more of those. Let's do these first. Okay, so here we've got the angles. And our rules for parallelograms, we would have to show that the opposite sides here are parallel. Well, to do that, we have to start with y, because the only approach we can take is that these two angles have to add up to 180 degrees. So we'd start there, and we'd say, okay, well, if these two angles add up to 180 degrees, that would be enough to guarantee that the top and the bottom, okay, are parallel. That would guarantee that we have one set of opposite parallel sides. So we'd start there, combine like terms. 4y plus 60 equals 180. Then we would subtract 60 from each side, which would give us 4y equals 120. Divide by 4, we get y equals 30. So once we have the y value, then we can find x, because if y is equal to 30, then this angle would have to be 124 degrees, because it would be 4 times 30 plus 4. Well, then we can turn around and say, okay, well then these two angles, they also have to add up to 180. So 7x plus 124 has to equal 180. And we can solve that equation by subtracting 124 from each side and dividing by 7, which would give us x has to equal 8. So we can do one and then the other. And what we've done by guaranteeing these values, by setting up these specific equations, is we have forced both sets of opposite sides to be parallel, and in return, we force that to be a parallelogram. Same thing can be done with opposite sides. If this is a parallelogram, then opposite sides have to be congruent. So that would allow us to set up two equations, one for x, 3x plus 4 would have to equal 5x minus 2, and one for y, 4y minus 9 would have to equal 2y plus 5. In both cases, we would isolate the variable. So in this case, subtract 3x and add 2 to each side. Over here, we would subtract 2y and add 9 to each side. So that gives us 6 equals 2x and 2y equals 14. In both cases, we would divide by 2 to get our values, and we would get that x would have to equal 3 and y would have to equal 7 in order for that to be a parallelogram. Okay, the third and final type of problem is a more advanced type of problem. And if you're in a regular geometry class, you may not actually do problems like this, but this is for my pre-AP students. There are several ways on the coordinate plane that we can guarantee that a quadrilateral is a parallelogram. We can do that using the slope formula, the distance formula, or the midpoint formula, depending on which test we run. So there's 3 examples here at the end of the notes. I'm going to show you how to confirm that a quadrilateral is a parallelogram using each of those 3 approaches, the midpoint formula, the slope formula, and the distance formula. So all of these problems are started off the same way, and that is you need to graph the quadrilateral that's being discussed. So here in this example, K is located at point 2,3, L is located at 8,4, M is located at 7, -2, and N is located at 1, -3. So we graph those points and we connect them with a straight edge to generate a picture of the quadrilateral. So here's the quadrilateral. That again is K, L, M, and N. And yeah, it looks like a parallelogram, but unfortunately for you, that is not enough information for you to guarantee that it's a parallelogram. So when we see using the slope formula, first of all, the slope formula is y2 minus y1 over x2 minus x1, or rise over run. So we can go in and we can figure out the slope of each of our 4 sides, and if we can show that we can show they're parallel by stating that they have the same slope. So if we can show that the slope of KL is equal to the slope of MN, that would be enough for us to guarantee that KL is parallel to MN. Okay, so we have to check that, because if that's true, then these are parallel line segments. The same thing can be said of the slope of KN and the slope of LM. If they are equal, that would guarantee that KN is parallel to LM. And if we can show that both sets of opposite sides are parallel, then we've got ourselves a parallelogram. So the downside is that that does require us to find the slopes of each of the 4 sides. So we just start in and we grab one side. Let's say we start with KL. Well, if we're doing KL, that means K is one of our points, x1, y1, and L is the other, x2, y2. And just like we've done so many times before in our algebra classes, we feed that through the equation y2 minus y1 over x2 minus x1, which would be 4 minus 3 over 8 minus 2, or 1/6. Then we do the same thing for M and N. Well, again, when we go to do MN, the numbers that we apply are different here. Those are no longer x1, y1, x2, y2 anymore, because now we're using M and N. So we'd have M as one of those points, x1, y1, and N is the other, x2 and y2. So we'd go in and we would say, okay, y2 is -3 minus y1 is -2, which is really +2. You know what, I don't want to write it that way. So -3 minus -2, which is really -3 plus 2. You feel free to skip to that step. And then x2 minus x1 is on the bottom. That is 1 minus 7. So you're looking there at -1 over -6, which is also 1/6. So we have confirmed that this is true, which means we've confirmed that KL is parallel to MN. Because these are equal, this is enough for us to guarantee that KL is parallel to MN. And we can go into the picture and we can mark that. It's guaranteed to be true. We've just proven mathematically that those are parallel lines. Then we do the same thing for the other pair. So KN. Now remember, as you're doing this, if the answer is no, if they're not equal and they're not parallel, you can stop, because the answer to the entire question is no. But unfortunately, if they're not equal, or if they are equal, we've got to keep going. So in this case, we would say, okay, well, x1, y1 is K, x2, y2 is N, and we do the slope. y2, which is negative 3, minus y1 is 3, over x2, which is 1, minus x1, which is 2. That's negative 6 over negative 1, or a slope of positive 6. Then we repeat that step for the last line, which is LM. So again, when we do that with LM, we've got to reset what our points are. And we have to say x1, y1, x2, y2 on L and M. So y2 minus y1 would be negative 2 minus 4. And x2 minus x1 is 7 minus 8. That also is negative 6 over negative 1, or positive 6. So again, the fact that these are equal, they're both 6, confirms this statement and confirms this statement. So this tells us that Kn is in fact parallel to Lm, and we can go in and mark those as well. And at this point, now that we've confirmed that both sets of opposite sides are congruent, we are now able to answer the question as yes, JKLM is in fact a parallelogram. So that's the way we use the slope formula. We confirm, using our first test, that both sets of opposite sides are in fact parallel line segments. Okay, our next example here asks us to do the same thing, confirm whether or not a quadrilateral is a parallelogram using the distance formula. So this one is going to be a little bit more taxing on you as students, but it's still nothing you shouldn't be able to handle. Start by graphing. A is at 3, 3. B is at 8, 2. C is at 6, negative 1. And D is at 1, 0. So graph those points, connect the dots. Excuse me, and label. Now, when we are confirming whether or not this is a quadrilateral, again, we've got to show, using the distance formula, which again we should have memorized because it is it's something we could use on the SAT, and it's not something that is on the SAT reference sheet. So the distance formula says the distance between 2 points x1, y1 and x2, y2 is given by the square root of the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared. So what we need to do here is we need to confirm that both sets of opposite sides are congruent. So we need to confirm if AB is congruent to CD. Well, the way that we do that is we check to see if AB is equal to CD, if the length of AB is equal to the length of CD. Okay, we do the same thing with AD and BC, which means we need to run the distance formula 4 times, once for each set of sides, in order to confirm that both sets of parallel sides are equal. So we start with AB. The length of AB means that A is x1, y1, B is x2, y2. And we plug into our distance formula. So x2 minus x1 is 8 minus 3, quantity squared. y2 minus y1 is 2 minus 3, quantity squared. That is something we can feed directly into our calculators, but that is 5 squared plus negative 1 squared, which would be 25 plus 1, or the square root of 26. That is not an even number, so we just leave it as a root. There's absolutely no reason to bother to turn it into a decimal. Then we do the same thing with C and D. So C and D are x1, y1, x2, y2, and we go in and we find the length of CD. Again, we're using that same distance formula, x2 minus x1, quantity squared, y2 minus y1. When we subtract negative 1, that really becomes plus 1, quantity squared. Well, that's negative 5 squared plus 1 squared, which is still 25 plus 1, is still the square root of 26, which means that confirms, okay, the fact that these are congruent, means that this is true, which means this is true, and allows us to go in and mark our first set of congruent sides. Okay? That confirms that AB is in fact congruent to CD because they are the same length. So then we move to the other two sides. We start with AD. So x1, y1, and x2, y2, and we plug into our distance formula. x2 minus x1, quantity squared, y2 minus y1, quantity squared. That's negative 2 squared plus 3 squared, which is 4 plus 9. That's the square root of 13. And then finally, we check BC. Remember, it should match AD if this is a parallelogram. So we have B is x1, y1, C is x2, y2. x2 minus x1 would be 6 minus 8, quantity squared. And y2 minus y1 would be negative 1 minus 2, quantity squared. That again is negative 2 squared plus negative 3 squared. So just like the other one, it is the square root of 13. Again, that is enough to confirm that AD is congruent to BC. And it allows us to go in and mark our second set of sides because we confirm those are equal, which means they are congruent. Combined with the other statement, that is enough for us to declare that yes, this is in fact a parallelogram because we have shown that both sets of opposite sides are congruent. Now you could also combine the slope and distance formulas to do one of these problems by simply showing that one set of opposite sides are both congruent, meaning run the distance formula, and parallel, which would run the slope formula. All right, the final test for parallelogram problem here involves the midpoint formula. If we're asked to use the midpoint formula, which is that x1 plus x2 divided by 2, y1 plus y2 divided by 2. It means we can find the midpoint of a line segment by averaging the x-coordinates and averaging the y-coordinates. So what we're doing here is we're checking the diagonals. Okay, what we're really doing is we're checking to see, do the diagonals have the same midpoint? Because if they do, then they bisect each other. And if they don't, then they do not bisect each other. So it's that simple. We go in here and we graph these points. So we have F is at negative 2, 4. G is at 4, 2. H is at 4, negative 2. And J is at negative 2, negative 1. So we graph those points and we connect them. And even though it doesn't really look like this is a parallelogram, we still have to check. So we have here F, G, H, and J. We are checking the midpoints of the diagonals. So we're going to do the midpoint of FH and the midpoint of JG. And if those are the same point, then we have ourselves a parallelogram. And if they're not the same point, then we don't. So we start with the midpoint of FH, which is one of our two diagonals. Remember that to find that, we're going to do x1, y1, x2, y2 on F and H, and we're going to plug those into the midpoint formula, which says we add the x's, divide by 2, add the y's, divide by 2. So the midpoint of FH would be 2 divided by 2, which is 1, and 2 divided by 2, which is 1. So the midpoint of FH is located at 1, 1. We would then do the same thing with G and J. So we do the midpoint of JG. Remember, this would have to be the same. So x1, y1, x2, y2, feed it to the midpoint formula, so add the x's together, divide by 2, add the y's together, divide by 2. Well, when we do that, we still get an x-coordinate of 1, but the y-coordinate is 1/2 instead of being 1. These are not equal, so our answer here is no. Okay? We've shown here that the diagonals do not bisect each other. If the diagonals do not bisect each other, because they don't share the same midpoint, that means that this is not a quadrilateral. So that would be a no. All right, that does it for section 6.3. Thank you very much. Good luck on your homework. Let me know if you have any questions.